Carolina Jauris. I am from Federal University of Santa Maria as Professor Koller. But I am experimental chemistry. So my talk will be very different from the other talks you saw during this event. Today, I will show you some technological applications of water, using water, a crucial molecule in the development and technical applications for sustainable nanomaterials. Well, we are here, Professor Koller showed, but I am the chemistry department. This is our 2 labs where we do the synthesis, characterization, and application of different kind of materials. But what is the relation between nanomaterials and sustainability? Do you know? Normally, we think about the development of nanomaterials since their origin from the reagents. Normally, they are obtained from mining and fossil combustibles. How it is produced? Major of the synthesis use a very large time, expensive systems, control atmospheres, reactants, and we also think about their applications. That can be what you're imagining. There are any kind of nanomaterials used to several applications. But we think also with the destination of the material at the end of the circle of life. But, well, we develop the materials, use it, but in the end, these materials you will dispose it in the environment. In the same way, they can become a risk. So water in the sustainable nanomaterials, how is its paper to solve these problems? Since the choice of reagents, and we choose the reagents from natural and national source inputs, mainly, to generate employees and economy. And we choose environmentally friendly sourcing routes, green routes, using water as only solvent as maximum as we can. We think in using these nanomaterials only for sustainable applications, clean water, sustainable agriculture, sensors, clean energy. This is the main application we do for our materials. And also, we are concerned with the nanotoxicity of this material because if we develop as real sustainable nanomaterials, we need to concern about the circle of the life of this nanomaterial. That in the end, when this material was disposed, it is not toxic. This is an important thing in a real sustainable nanomaterials. So our nanomaterials are planned always respecting the principles of ODS goals, the Sustainable Development Goals. The main goals we seek is this 4 goals. We have different kind of studies, and today I will show some few systems combined with theoretical calculation to explain what we see in our nanomaterials. Our group work with the sustainable nanomaterials and multifunctional, because when we do a nanomaterial that are multifunctional, we can use a same material as sensor, as to clean water, and to storage energy. So this is a kind of material that is multifunctional. Being multifunctional is sustainable. We do the synthesis, characterization, and application, and evaluation of nanotoxicities. Our main concerns are with environmental remediation, energy generation storage, geosynthetics, and sustainable agriculture. Here we do a lot of characterization, but this is experimental thing. But we also explore the basic science behind every process. Today I will show you some few examples. The main that are related to development of graphene-based materials for multiple applications. I will focus today my talk in removing emergent contaminants from water. Everybody knows, everybody see that 2D materials like graphene, graphene oxide are excellent candidates to remove, to clean water. But 3D graphene presents several advantages compared to the 2D materials. It has low density, high porosity, high surface area, super hydrophobicity, but this material for environmental application have increased advantage compared to the 2D materials, because the traditional 2D materials, you use 2D materials like a membrane of graphene, this kind, they are in real world, they are not safe, because its sheets can be displaced of the membrane and act as a nanopollutant. So it's not safe using like this. So in our material, we choose develop 3D materials like the graphene sheets are connected covalently like this, like a hydrogel, a aerogel, or different kind of materials we can do using covalent bonded graphene sheets. The traditional methods to obtain this kind of materials needs several steps, high costs, use of templates, time-consuming synthesis, and most of them tox reagents. Our goal is solve this problem, producing 3D-based materials with low cost, rapid, in a quick synthesis, and in an environmentally friendly synthesis way. This is a method we patented. A general approach starts from the natural graphite, natural Brazilian graphite. We do a chemical synthesis oxidation where obtained the graphene oxide dispersions. These graphene are dispersed in water. We use a conventional autoclave that used in a medical or in a optic to clean glasses, also in the nails maker, the simple autoclave, ship autoclave, using only 2 hours, using C vitamin and other reactants extracted from the trees, natural extracts, to reduce this graphene oxide and transform in 3D reduced graphene oxide hydrogels. We have this kind of materials in the end of the process. This synthesis is no expensive, no needs complex reactors, and are at least 12 times quicker than the conventional methods described in the literature. So we patent this, only use water and natural reactants. Using this approach, we can modify the synthesis and obtain different kind of 3D materials, use different reducing agents, different proportions of graphene oxide in reducing agent, inserted metal ions as precursors for the formation of nanoparticles, and also we can insert monomers of polymers to create a 3D with polymers adhered to this surface, and we have a different kind of applications for this. This is the material. They are well cohesive and self-supporting structure. Here is a hydrogel. The pores are filled with water. When we dry it, we have aerogel. The pores are filled with air. This cylindrical shape is because we use a beaker during the synthesis, but we can modulate the synthesis using, if I use a LMR flash, I have this kind of structure. If I have a Petri dish, we can have membranes, thin membranes like this. And we also characterize this for several experimental techniques to understand its structure and size of pores, the functionalization, and we have different kind of materials. These materials present a high surface area, pores from few nanometers to micrometers, low density. To see, we have here a flower of a basil. It's a tiny flower. We have our material, a dried material, inside this flower. This flower remains intact. It's so low density material. And these materials present a thermal stability until 600 degrees Celsius, very high. These materials, we can nano-architecture this structure only by choosing the amount of reductive action. The reductive action we use to remove the oxygen, connected the sheets, and transformed it. Like this part is less reduced, so looks like graphene oxide. To here, we have a more reducing agent, and a material looks like the graphene structure. But all the materials are very porous. We can modify the nanostructure. With the amount of reducing agent, we have a more compact structure, so the sheets get closer. And we reduce the amount of functional oxygenated groups, and we can design the material according to the needs to application. The main application is for environmental remediation, where we study the removal of metals, dyes, nutrients, oil, pesticides, some drugs, and desalination. To this, we test several factors that can influence this adsorption, like pH, ionic strength, temperature, functionalization, the amount of groups, and the different kind of absorbent and absorption proportions. The first work I will show you is work to remove phosphate from water. Phosphate, if you know, is a nutrient, is an anion that when it is in a higher amount in the water, it causes this problem called eutrophication. Eutrophication is when the algae arise in a high amount and cause the death of fishes in the environment. We test these different materials, more oxidized and more reduced, to remove this phosphate. We change the different, in different mediums, change the pH from an acid to a basic medium, ionic strength, since a low ionic strength, mimetic a river environment, to a high ionic strength, like a sea environment, and changing the temperature from a temperature in a cold place to a higher temperature in a tropical, streamy environmental place. We show that dependent of these parameters, we can remove more or less phosphate, but always removing more than 85%. It's a high amount of phosphate removal. So we can show that the material can modulate according to the environmental to be treated. If I want to remove phosphate from a river in a cold place, we can design a material specifically to that. But if I want to remove phosphate from a seawater or salobra water, we can design the material in a different way to remove in that place. The materials are very well also in the real world. We test in a eutrophicated lake in the reduction of more than 86% of a very high phosphate content in all the systems evaluated. But we need to understand why. Now we use the acknowledgement of our friends, theoreticals, Patrick and Mateus did this calculation to us, and we try to understand why this phosphate can be removed. We use dynamics calculation, and we discovered that the graphene functionalization membrane is mediate water purification process. So when we are, they explain when you have a more oxidized sheet in the graphene, the phosphate is attracted to these layers more than when we have a reduced material. Also, we show the formation of potassium shell around the phosphate, the contra-ion, strongly suggests an aggregation. This is a new information that we never saw in other works. This shows that it's not only dependent of the nature of the graphene materials, but also the contaminant we need. So some contaminants aggregate, others no. So we need combine the pore size, functionalization of the pore, and the nature of the contaminant. We also saw that the interlayer distance was a determinant factor for the absorption of the ions and molecules. So the material with more porous material and more functionalized are better to remove the phosphate. Also, we use DFT calculations, and we see the impact of the temperature, and we in agreement with the experimental data, we saw that the decrease in energy highlight the smaller phosphate clusters, and the absorption is energetically favorable. So if we have a higher temperature, we avoid this aggregate formation, and we can enter in the pores and keep absorbed in the sheets. To prove the formation of this aggregation, we use Raman and infrared spectroscopy. We saw this different kind of vibrations. We lose some vibrations of phosphate and appears another vibration. This proved the theoretical results that we are aggregating the phosphate. So this is a very nice and complete work we published this year with these guys. So we established a very well complete mechanism why we can remove phosphate from water using these materials. Another system is using dyes. We have different works using cationic, anionic dyes in different environments. And today I will show you this is a methylene blue high concentrated water solution. And we are dropping in a membrane, this material, with a flux. It's a pumping. And we can see the higher is very, very blue in the beginning. In only 1 minute, we can absorb and transform this high concentrated pollutant solution in this, in 1 minute. So it's a very, very interesting. But we have a problem. When we saw the different kind of materials, this is the start. But when we read the behavior of these materials, there's not a linear behavior according to the amount of oxygenate group. We saw these intermediate materials floated and absorb more than the more oxidized and less oxidized. So we need to understand why. Why this? So we use the knowledge of Bordin Lab, Professor Bordin, and Professor Solange Fagan from UFN to understand using dynamics and quantum calculations why this was happening. We discovered that the simulation indicates that the absorption of the methylene blue in graphene oxide and in graphene pores is a combination of two main factors. The pore must be large enough. These two intermediate materials are more porous. The pores are intermediate materials are huge compared to the other two. So our materials, they have pore much large enough to the aggregates. Again, this material, this methylene blue dye, form aggregates. And when we have pores, huge pores, these aggregates enter and can be absorbed in the graphene sheets. And the existence of oxidized sites facilitates the absorption in the walls. So again, it's a combination of these two main factors, looking for the material and the aggregation possibility, looking for the contaminant. So we break a traditional thinking that is the higher absorption in graphene sponge materials are related to this high surface area. Not necessary. We did a very systematic review we published, and with our studies, we showed there's no direct relationship with the surface area and as previously believed. And the adsorption contaminants are related not only to the surface area, but rather the size of the pores, the presence of functional groups in the material, and mainly depends of the contaminant structure and its ability to form clusters. This is a break in the previous believed knowledge about adsorption in materials. Well, we have some open systems for students. This is a work for some of you. We test the heavy metal removals. All the materials remove higher concentrations of the several metals. I highlight the plumbum. Plumbum is a record of adsorption in this kind of materials. It's a high concentration. But the adsorption is different depending on the metal. We don't know why this happened. There's no a linear behavior. But we saw, again, it's possible to control the selectivity of the materials for a specific metal. So if we have a contamination with zinc, I can choose the less oxidative materials. If you have a contamination with plumbum, I can use the more reduced, for example. So I can design the material for a specific environmental problem. Bordin did some calculations to explain for copper, and we saw when we increase the oxygen contents, it's better the absorption and desorption on copper. This is an important thing, not only absorption, but the desorption to recover the material is a request for a real application. But now, Rafa, we need to find out what the effect is of the nature of the metal and the distance between the plates. This is it's a challenge for you and Patrick. Patrick, now I need to understand this. It's a very interesting, some questions we need to answer. And the materials, again, we test in this lake is a mining for copper lake is a blue. The amount of copper in Rio Grande do Sul is a desactivated mine is huge. So we are able to remove a lot, more than 50% of the high concentration of copper, plumbum, and strontium that are minerals rich in this region. Another gap we need to explain is this. We test for desalination. So we test these materials. We saw the materials more porous. Now they are worse to desalination, different from the other materials for the other contaminants. Now they are worse. The best material to desalination is the more oxidized and porous intermediate. Why this happen? Marcia, yeah, you you need to solve. So the question that we need to explain is what's the effect of presence of oxygenate groups? Why can a negative charged material remove an anion so well? Why? And what's the effect of the size of the pores? Again, these are the three questions we need to explain. Another system, to improve the different properties of these materials, we decorated this 3D graphene-based materials with nanoparticles. One of these nanoparticles was with silver. Why silver? Silver is interesting for sensors, bactericidal, and for storage energy, and this is why we insert silver in this material. But the preliminary study was try to understand what is the effect of the reagent addiction sequence if I add first a surfactant or first a metal, what this can change in my material structure, and what this can change in the properties of these materials. We only change the order of the sequence of adding the reactants. We have different kind of materials with more or higher nanoparticles into microparticles, whites, cubes. Some materials present cubes. Some materials present spherical nanoparticles. All these materials present high thermal stability. Again, we have this kind of nanoparticles are mainly pure silver nanoparticles and silver oxide core shell nanoparticles. But we need to understand why some of these materials present this kind of structure where the nanoparticles are in the winkles, mainly in the winkles. Why? So Bordin did some calculations that help us to understand when we we add firstly a surfactant molecule. The surfactant interacts first with the graphene sheets, hindering the addition of the nanoparticles. And the consumption of this surfactant avoid the control of the size of the nanoparticles. There's a competition between the graphene and the nanoparticles for the surfactant. So we have materials with bigger nanoparticles. And when we insert first the precursor, the ions from silver, we can form nanoparticles, and mainly in these winkles, these regions, because their interaction, the energy we have in these winkles, and we have smaller and well-controlled, well-positioned nanoparticles. These materials we test for sensors to analyze contaminants like pharmacs in low concentrations in the environment, and it was very well with low quantification limits. Here we also, many of you can saw the work of Bruna, my master student, that she used this kind of graphene decorated with iron. We test this for degradation as catalyst for degradation of caffeine, but now we are testing this material to remove fluorine. Fluorine adsorption, the first results show that records for adsorption in fluorine, but also we will need to understand why. How we can adsorb so well this fluorine more than chloride. So this is a gap we need to estimate why chlorine adsorb more than another halogen ion that's chloride. And then this iron nanoparticles will be used to electrochemically recover this fluoride, again, recover the material, the adsorbent. The new system, in the last part I will talk, is self-organized hairy gold balls. We show, hairy gold balls is nanoparticle functionalization with ionic liquids. Ionic liquids are organic salts that main liquids in above 100 Celsius degrees and present several incredible properties. We use this ionic liquid here to passivate and stabilize nanoparticles. We have here a dispersion of gold nanoparticles is a beautiful red solution. And we use this to form films. We drop casting, form different kind of films. And our main goal is use these films to a sensor in low concentration of contaminants and some tumor marks to with the goal to in concentration in parts per trillions in time to initiate early treatment for cancer or environmental remediation before this concentration of this contaminant become a risk. So you use this Raman enhancement to use it's a technique that uses a plasmon surface of the gold to increase the signals and detect concentrations in part per trillion of the molecules. What's the problem? When we dry in different conditions, we have different morphologies of the materials. When we dry, we have two materials with more ionic liquid and less ionic liquid, and we try dry this to sulfur assembly in room temperature and an oven with more concentrate and also in room temperature and over dried. But in all these conditions, the morphology was completely different. Completely different, and this completely different morphology affects how sensitive is the search sensor. And we don't know why. This, we see this atomic force microscopy. We can see a small piece, look in there. We have different self-assembly. When the same material dried in an oven with more ionic liquid, is a plaque, is a continual plaque. But when we have less ionic liquid, we have this particle assembly like shells and layers, different layers. This is a very interesting kind of arrangement and affects directly the sensor. Here we have the materials again dried in room temperature. We can see the particles recovered by the ionic liquid. And here the material, the same material dried in an oven. It's completely different morphology and different properties. So the gaps to solve, we need to understand how the ionic liquids contain the nanoparticles can self-organize in this different surface as function of the concentration of the ionic liquid, film drying temperature, and what is the effect of this organization in the search sensor for detection of the different molecules. Well, we have some financial supports. The partners, the most important are here. Thank you, guys. Thank you, Marissa. Some industry, we have a lot of other projects using residues from the agro-industrial to transform it in technological materials, but we don't have time to discuss this. And this is my actual team. Most of them, we have, Bruna is here, we have my undergraduate students, my doctor's students, and thank you for listening. Questions?
The first systems in which you just have carbon, how the results dependent on the structure? You produce one sample, it might have one structure. You produce a second sample, it might have a different structure. How is your result dependent on these differences?
The materials, from a synthesis to another, they are very comported. They are reproduced. But when we change the amount of the reducing agent, the amount of the force that we can remove the oxygen group, we change the structure. First, when we don't use a reducing agent, we have a material like crumpled graphene. It's a sheet of paper smashed. We have this kind of structure. When we insert the reducing agent, we are with low. We have the distance between the sheets higher, but we have also a greater amount of oxygen remaining groups. According, we increase this amount, we are compressing the layers between the graphene, and we have less these groups, and more interconnected, more covalently bonded graphene sheets.
You mean that you can control the layering distance, the interconnections by the
Yes, the methodology only changes the temperature, the time, the kind of reducing agent. We can nano-architecture the material. This is a very nice thing. If I insert, for example, a monomer, I can put a polymer between graphene, polymer, graphene, and we have a super absorbent. It's a material very, very new and very interesting. That we use also to capacitor and use to a sensor. And a sensor for gas and a sensor, electrochemical sensor. One material, we can have multiple functions. Mm-hmm. No, 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 there's no order.
Can we assess like a mean distance, like average distance from the experimental point of view, or there's?
Yes. We use BAT, surface area measurement. We can measurement using normally nitrogen gas. We know the amount of molecules we insert in the system, and we can calculate using pressures and some mathematical artificials. And we can discover the size of the pores. We have a histogram to since the smaller to the higher median about these values. The surface area, and the main this effects and another characteristics using this technique. Yes, we have this data. We have this data.
Well, I think it depends on many things, but how you calibrate distances by inserting ions, things like that changes the distance.
We can change the distance only controlling the amount of reducing agent or the temperature, or another way is freezing before the graphene oxide and heat slowly to keep. When we dry the material, according to the way we dry, we can have more pores or like an aerogel or a aerogel material, different hardness also materials we can control only by synthesis. Any more? Curiosities? You know? You can saw more of our work in our Instagram, in X No More, but we have some. Thank you.
Mais inteligente. Ué, fecharam o Google Chrome? Okay. So let's finish everything so we can go to the parade. Yeah. So again, first of all, thank Marcia and the organizer for inviting me to talk here. So I'll talk about something a little bit different, but that Marcia told a little bit yesterday. There's basically core soft models and how we can use this to understand not only anomalies, but another properties that you can observe in water and other models as polyamorphism and polymorphism. So, okay, I am Rafael, for who doesn't know me. I am from Pelotas, is almost in Uruguay, almost falling from Brazil to Uruguay. So it's a really nice city. Unfortunately, the beach is not so beautiful as it was due to the floods. But well, we have a nice architecture, we have a nice beef, we have great sweets to to eat in Pelotas as well. So please go. You can go to Pelotas to eat a lot of great food. And I am from the Federal University of Pelotas. This was one of the first buildings of the university. Despite the fact that we are now, the birthday was last month of 55 years. Actually, the agronomy faculty started in the 19th century, so it's a really old university, really old for Brazilian parameters, obviously. So this is the building where we are right now, but this picture is from the 70s. Okay, so this is my group. Basically, we will not talk about the work of any one of them today, but there's a lot of people working. Some of them are here, like Davi, Patrick, and Lucas, this guy, but there are a lot of people. I have serious issues, and I work with a lot of different stuff. So I work with nanomaterials, I work with fluids, including water, social physics, colloidal systems, and biological and medical physics. And well, I'm working with this with my therapist, so I can be a little bit more focused. So, I will not talk about anomalies because we are probably heard a lot about it in the last 4 days, but well, water has a lot of anomalies, density anomaly, the fact that ice has a lower density than liquid water, there is the diffusion anomaly, there is the viscosity anomaly, and probably, I don't know if anyone showed this graph, they showed? Anyone? No? Okay, and so water has this kind of hierarchy of the anomalies. So if you make a plot, temperature against density or temperature against pressure, you will see that you have the thermodynamic anomalies in one region, and then you have the dynamic anomalies, like covering the thermodynamic anomalies, and above all, you have the structural anomalies. So we can try to see the region in the whole T or PT phase diagram where water has this kind of anomalies. And why water has these anomalies, also you heard a lot of people talking about it. It's basically related to the fact that water is not only one liquid. It has two personalities, one with low density personality, another one with a higher density personality. And this personality keeps struggling. And so you have this, this phase transition that we believe that's true, but we still doesn't have an experimental, how can I say? Anyone ever saw this in experiment, but a lot of theoretical physicists and chemistry already saw it in simulations. So we believe that simulations are working well and are correct. So basically water, also, I don't know if Paola showed this review, but if you never read this review, you should download it right now and read after my talk. So it's a really nice review, and basically the idea is that the anomalies of water, they are related to the liquid critical point, and this liquid phase transition can be related to a glass transition between a low density amorphous water and a high density amorphous water. So this is water. I will not talk about real water. I will talk about a more simple system. The idea is basically that what Marcia told you yesterday, that you have a high density water where the tetramers are close, and a low density water where the tetramers are a little bit further one from each other. So the simplest way that we can imagine this kind of system is a two-stage system. Physicists do this for a few centuries. The Ising model is a two-stage system, up or down. Here, we have a two-stage system. I want to get close, or I want to get further. And, well, and the idea is try to use this kind of system to understand what's happened here. And, sorry. And, oh, yeah, and the people are trying to understand this for quite a few years, since the paper by Stanley in 1992. There was literally a war trying to prove the existence of this liquid critical point, because the two main groups that study water in the world, one was saying this liquid point exists, the another one was saying no, this liquid point is just an artificial result from simulations, and was like an 8 years battle in struggling and publishing a lot of papers. And at the end, in 2018, they found a mistake in the code. And so the liquid-liquid won the battle, the liquid-liquid transition. And we have some evidence in real water of this phase transition that's basically the Whedon line that also was talked yesterday from Paola, so it will save me like 5 minutes of my talk. Okay, so how we can get water and make it simple? And I want to say simple when you want to model it using an effective model, a two-state model. So in 1993, Teresa Head Gordon and Frank Stillinger proposed they proposed this potential for water. They basically took the G of R between the oxygens for experiments. They applied this to the Ortiz-Zernick equation, and then using this thing's closure as the hyperneck chain closure, you can get this kind of spherical cold water. So you have an effective potential that you can model water, and this kind of simple equation or simple potential can reproduce most of the anomalies of water and the liquid-liquid critical points and other properties. So going now for something completely different, I will not talk only about water, but also about another system. A long time ago, in the 70s, these two guys, Hammer and Stell, they were interested in studying microgels. What are microgels? They are like fluffy balls of polymers. So when the two of these guys get closer, you can first have the repulsion between the polymers, but you press it a little bit, they are fluffy, they can get even closer. So you also have this kind of two states. Further state with the microgels getting a little bit apart and a closer state. So they propose this kind of potential with basically two ramps. So you have this repulsion at lower distance and a kind of attraction at bigger distance. What was really interesting is that they find that controlling this property of the potential, you can literally create extra phase transitions and can literally create extra solid phases or even extra fluid phase as water. Remember, water has two fluid phases, or two liquid phases, sorry. 3 fluids, 2 liquid phases. Also, water has more than 20 solid phases. So it's an easy way to try to create this kind of polymorphous materials, or materials more than one morphology for the same phase. Please wake up Luana for me. Hi, good morning. Eu estive dormindo. Okay, and well, 20 years later, or almost 30 years later, another guy that you also heard the name yesterday, Paulo said Jagla, we say Jagla, is a guy from Argentina. He used this potential, it's a really simple ramp-like potential to study this kind of core collapse particles. It's the same idea. So we have repulsion, but not so strong repulsion at a longer distance, and then you have this kind of ramp, and you have a really strong repulsion at shorter distance. And this creates this idea that the core can be collapsed, so you can, the particles can penetrate a little bit. And he found a lot of solid phases, 2 disordered phases, 3 two disordered solids, or 2 amorphous solid, 3 ordered phases. So you have the polymorphism, the polyamorphism, more than 1 amorphous phase. And also, if you add here a little attraction, you can have anomalous property of water. You can have the liquid crystal point. As Paola said yesterday, that they use this model to understand the liquid phase transition of water and to see if the transition is Ising-like or not Ising-like. Okay. So why I was saying that I will talk about something a little bit different, because this kind of potential can not only be used for microgels, but also for another kind of particles. If you start for a hard sphere, it's a hard sphere, so you basically have a really strong repulsion when they both get close. So a kind of infinite barrier. But if you soften this particle as a vesicle or even, as Carol said, a hairball. It will get softer, and then you can have another kind of potentials to model it. So this was kind of the inspiration for a work that we did a few years ago with contribution of two former students. One of them is Thiago. He's now postdoc and, well, making more money than myself here as with the FAPESP scholarship. But, OK, we took this kind of model and we make a coarse-grained model. So it's not an atomic simulation. It's basically pick up a bigger sphere in the center. You put a lot of polymers around it, make a lot of simulations, and we evaluate the G of R. From the G of R, we use the Austen-Zernike equation with the hypernet chain closure, and also the inverse Boltzmann procedure, where basically we say, OK, we want to get this G of R. So we try to guess a lot of G of R's. This is the GI, to reach our G target. And with this, we can get this effective potential. So we use the idea of a Lennard-Jones plus a lot of Gaussians. Why we use this idea, we will see in the next 2 slides, I believe, or 3. But essentially, here in red, you have the exact result from the inverse Boltzmann procedure, and in black is the approximation using this potential and some parameters. And so we apply this. Another student involved in this work was Murilo. He's a professor in the Federal University of the West of Bahia. And basically, here we have our effective potential, the kind of patterns that you get. Here is the coarse-grained model, and it's basically the same pattern at the same density and temperatures. So it works really well. And also, we have in the system some water-like anomalies. So we can literally create nanoparticles that can have water-like properties. And it's really fine, and probably it can have some kind of application in the industry. But, well, this will be for the experimentalist or applied physicist. OK, and why we use the idea of a Lennard-Jones plus Gaussians? Because a long time ago, Marcia showed this potential yesterday. They proposed this model to try to understand the water anomalies. So it's a really simple model, really effective model. And the idea is that you can have remember the hierarchy. Here is the TMD, the density anomaly, or the thermodynamic anomaly. Here you have the dynamic anomalies, the diffusion, minima and maxima. And here you have the structural anomaly, both translational and orientational anomaly. And what they saw is that these anomalies are related with the competition between the two scales. So in this model, the molecules can get a little bit further or a little bit closer. If your pressure is low, for instance, you'll get mainly at this distance. If you increase the pressure or if you increase the temperature, you have enough energy to climb the ramp and get to this another state. So we can see this competition in the G of R, and the second length scale, the population here goes down, and the population, the first length scale, goes up. And this explains the anomalies, this competition between two scales. But one thing that's really, really important, this potential is pretty repulsive. This is a main ingredient for this part. So in the end of 2022, every December, we make a meeting, basically Marcia and all of his son, grandson, and great-grandsons, and everybody. And then I was take a coffee with Leandro. He was my colleague in my PhD. We are friends since then. And, well, we'll talk a little bit about everything. So, and we go in this direction. OK, so supercooled water, it has the liquid critical point. And we believe that for real water, this is what creates all the anomalies. But if you have a pretty repulsive potential, you cannot have critical points. So that potential does not have a liquid critical point. So what was the question? There is any kind of connection between the anomalies and I don't know, maybe solid or amorphous phase for this pretty repulsive model. And why amorphous phase? Sorry, because remember, in real water, we believe that the liquid critical point is connected to the transition between the two glassy or the two amorphous water states. So what we did, a lot of simulations from the same model that Marcia and Alain, and Paulo and Thiago studied in 2006. Obviously, right now, almost 20 years later, we have much more computational power. We can run much larger and longer simulations to build the phase diagram. So remember, the idea is to try to build this kind of phase diagram. So first, to see whenever you have any kind of phase transition or the thermodynamic behavior, we can evaluate the specific heat. We did NPT and NVT simulations to map all the system. So we can see, for instance, that some cases you have a huge discontinuity in the CP, and another case is not exactly a discontinuity, it's more like a maxima. In CV, we saw the same kind of stuff in this almost the same temperature. Here is around 0.1. Here is also near 0.1 for the same density and same pressures. Well, what is nice, because the NPT simulations we did using a package called Espresso, and the NVT simulations we did using the same program that Leandro and I worked in 2010. And you know that that code was right. So we can compare both. We also evaluate the another thermodynamic functions as the expansion, isobaric expansion. Thank you, thermal expansion coefficient, and the KT, the isothermal compressibility. And here also we found something really, really nice. At really low temperatures, remember, this is an effective model, all the units are reduced units. You can see that here for the lower pressure or lower densities, you have a kind of discontinuity with this point going up, but here is more like a bump, more like a maximum for a little bit higher temperatures. Obviously, we'll try to understand what this happened. But we have the thermodynamic anomalies. Here's the TMD. We also get the minima in the alpha P. And when we go back to the KT, here I'm fixing the temperature, increase the pressure. So if I'm trying to build, remember, a kind of phase diagram, here is temperature, here is density or pressure. I can go by two ways. If I take, for instance, the specific heat, I do, sorry, this kind of analysis. So I go up. If I take the KT, it's like, okay, I'll fix my temperature, I will see what happens as I walk on this way. Remember, thermodynamic path. And what we found was that all of these discontinuities are related to basically phase transitions from solid, BCC, to an amorphous phase, then another solid, HCP, and another amorphous phase at higher pressure or higher densities. We map these transitions by structural properties as the excess entropy that I believe no, Paola told yesterday. I don't know if anyone talked about the structure factor. No, right? Yeah, but this guy is basically integration of 1 minus the G of R, if I remember well. It's something like this. What's the idea? If the G of R goes to 1, this guy will have a gas-like behavior, so we have a lower value because 1 minus 1 go to 0. And if you have a well-structured system, these guys go up because we have 1 minus something that's different from 1. You get a and you get the absolute value, so this guy increases. This is the reason, because when the entropy goes down, these guys go up. But they both gave the same information, and they're both based in the G of R. So we can see the distinct phase, And also we can understand a little bit about the long-range behavior. Okay? Because if you evaluate this, the cumulant of the excess of entropy. Remember, the excess of entropy give me information about how different my entropy is from the ideal gas. If this guy goes to 0, I am in a gas-like state. If this guy starts to increase, I go to a more ordered state. This is the idea. And it's funny because if you look for the HCP for the second amorphous region, the GFR at short range are really, really similar, but they are different at longer range. So we have to understand what happens in this longer range. And to understand this, we evaluate the cumulant of the entropy. As the name said, we are accumulating the entropy as we go to a further distance. So if you have a well-defined structure as in a crystal, this guy has to increase, as this black guy here. But if you have a disordered state, as a fluid or a amorphous phase, you reach a plateau, like this guy here. So this allows us to see wherever our system is a solid phase, well-structured, with a long-range structuring, or when we have some kind of short-range structuring, as in an amorphous phase. Okay, we will also evaluate the orientation of parameters, Q6 and Q4. And we can see, this is really nice. When you have the BCC to fluid transition, the orientation of the molecules change completely. So this Q6 and Q4 basically give me an idea about the number of neighbors of each molecule and the orientations of them. So you can see that when I go from a solid phase to an ordered solid phase to a fluid phase, they are really, really different. When I go from an amorphous phase to a fluid phase by heating the system, they are practically the same. What's happening? Basically, they are gaining mobility as I go from the amorphous to the fluid phase. I will show it later. But the system also showed the structural anomalies, as Marcia and Alain saw almost 20 years ago. And as I said, what was happening here on the left is the transition from the BCC phase with a low MSD to the fluid phase with a higher mobility. Here, HCP to fluid phase, you can see there is a huge gap, as expected for a first-order phase transition. Here we have a kind of second-order phase transition. There is no gap. As I heat up the system, you can see that my MCD starts to increase. But in the amorphous to fluid phase, there is an indication that is a second-order or continuous transition. And well, this is just the diffusion coefficient against temperature to show how it decreases. In some cases, you have this go straight to 0, and in some cases, more smooth in the amorphous to fluid transition. And here is the diffusion anomaly. We increase the pressure, and the diffusion increases. Okay, so, in a long and hard work, analyzing a lot of points, we built this nice work. So, and it's nice because it was published in the Emerging Investigation Special Collection. So I'm now not a young anymore. I'm now an emerging investigation. Sometime, a few years, I'll be an old investigation. And it's funny because Marcia is a young investigation up to date. So I'm not young anymore, even Leandro. And well, this is the phase diagram, the complete phase diagram. Each gray point was one simulation, independent simulation. You can see here the solid phase, the ordered and the disordered phases, all the anomalies. Here we pick up the discontinuity or the maxima in CP, CV, alpha P, and KT. You can see that it separates the phase. But what was funnier was these two guys here. Remember the bumps in the KT? He looks that it is going, is leaving the BCC from the amorphous solid transition, and it goes up to the fluid phase. Exactly where all these anomalies, the maximum in the diffusion, the maximum in in the structural anomalies, they all go to this point. And this was really nice. And obviously, we try to understand. Here we have a jump, and here we have this kind of bump. What's different between these two cases, between the bump or between the discontinuous regime? So we go back to the orientation of the system. So here, and also the translational order that you can analyze by the G of R. So at the low temperature in this transition, we can see that we have at lower pressure the BCC well-ordered phase here in blue. And as I cross the transition at the pressure of 0.86, you can see that this little guy, the first length scales, start to grow. And the system goes to the amorphous state. If I analyze the G of R now here in this isotherm, you can see that, the fluid phase at the left of this point, this blue system, is a little bit more ordered, and I go to the other side, is a little bit more disordered in the long scale. And more interesting, this guy looks at short range a little bit more like the BCC, and another one a little bit more as the amorphous phase. And also, we could see that here is the Q6 against Q4, the orientation of the system. If I go from the amorphous phase to the HCP solid phase, or for HCP to the another amorphous phase, these two cases here, you can see that in one phase, you don't have any point, how can I say, on the top of the other one. We don't have this overlap of points. Important. Each point here is the Q6 and Q4 for each molecule in our system. We was using 10,000 of particles, so we have 10,000 points here. So it's not the mean value, it's the value for each particle along simulation. So you can see that here you don't have any kind of overlap. If I take the probability of my system has a value of Q6, you can see that one phase is here, another phase is here, they are pretty well separated. But when I go to the BCC, to amorphous solid one phase, and I take the pressure at the left of this point and the pressure at the right of this point, you can see that these are some kind of overlaps. And more instance, if I take the probability, you also can have this overlap here. What was our guess, and that the reviewers and the editor accepted, was that these anomalies in this behavior and all this start with this amorphous clusterization in the solid phase. And we did not observe this amorphous clusterization in the another phase transition. So we have this competition actually between a fluid with a BCC-like structure and another fluid with a amorphous-like structure. And it's also obviously this is not the Widon line because the system does not have critical point, but it's a similar signature. Okay, we also did some work with 2D and almost 2D system, and this is interesting because it's connected with what Carol was saying in the end of his talk about the patterns that we can get in these Hairy-Ball systems. And okay, and if you have only one layer, for this specific potential, we can have a low-density triangular phase, this kind of stripe or labyrinth phase, a Kagome crystal, or a high-density triangular. And a really nice finding that we published this year is that if you allow the system to have not only one layer, but two layers, you can create new phases that you did not observe in the peer 2D system. Here, we create a square-like phase. So we can control the shape, you can control how these particles aggregate, or the morphology, basically controlling the dimensionality of our system. Also, we can create really simple model, even more simple than effective models, using DPD simulations. DPD is similar to molecular dynamics, but cheaper. So we are using an even cheaper simulation using the same idea of a double ramp interaction, but this is force, is not the energy. And well, this is the phase diagram, and it's nice because this phase here is a gyroid phase. And actually, it took me like 3 months to finish this paper because I could not understand what the hell was this phase. The system has the HCP, solid phase, a BCC phase, a cubic diamond phase. It shows the 3 amorphous phase, low density amorphous, high density amorphous, and very high density amorphous. And this phase here, just return, is this one. And it was published in 2022 in Nature, where they found for the first time this kind of structure. For this reason, was really hard to me to say what the hell was this. But this is basically a colloidal crystal that the people are really interested right now. So the idea is that you can use simple models that will allow you to perform simulation for the whole phase diagram and understand almost everything, try to extract information from this simple model to real life. This is the main idea. And obviously there's a lot more work to do, but I like to finish with 3 phases my talks, and also because I have a lot of students here. So just to remember, first of everything, okay, people who heard my talks the last years already saw this quote. Remember that academy is not paradise, but learning is a place where paradise can be created. So we have to fight for the university, we have to fight for the knowledge. And obviously this fight is an utopic fight. I will not say that we will win in my generation or your generation, but we need to keep going. And this quote by Fernando Birri, but it was Galeano who said and make it famous, is why we must to keep going even in an utopic fight, basically because the utopia is what makes us go forward, and it's a goal that we'll never reach, but we must keep going and try to reach this goal. And mainly, now talking about a Brazilian, Paulo Freire, remember that hope, hope is necessary, but it's not enough to achieve this. So we must have hope to get to this utopia, to fight for the university, but we need to fight, and fight with hope. So I want to thank you again, Marcia, and the ICTP-SAIFR for the invitation. Remember that without public funding, any of this research will be possible. So thanks NPQ, CAPES, and FAPERGS, and thank you very much. And questions? DPD? Yeah, because DPD, I already performed simulation with 500, 500,000 of particles in a desktop. And what was the problem? That the people use water-like molecule of water in DPD simulations, but this water doesn't have any properties of water. So I decided, okay, let's try to make a model that will have water-like anomalies. And in the end, it was much more interesting than my first guess. And also, we can control the shape of these forces. I literally just guessed these values of 10 and 50. Why? I don't know. It's just a guess, and it worked as well. But the idea was to create a DPD model that has water-like properties. And it's funny because I published this paper, I don't remember, I believe it was like September or August last year. And after I published, I saw another paper from Software Matter that, like for July of last year, that they are trying to do the same stuff. Create a DPD model for water with water-like properties. So with DPD, we can simulate systems with the size of micrometers with time like seconds, and well, and we can go to real life size. This is the main idea. Yeah. See, the DPD idea, remember, if you go to traditional molecular dynamics, the force acting in all the particles is basically from the potential. In DPD, we add two another terms. The first one is basically a friction, and this depends on the relative velocity between the two particles. So you have hydrodynamic effects. And also, you have another term that's basically a white noise, a random noise that basically you kick your particle at each, I don't know, 10 steps, then you can define this density. So with this, and if we here, we actually have a conservative force, usually. And the idea is that this conservative force always have, or usually have, this hump-like shape. So if you use a time step, a huge time step, and if you have an overlap between your particles, for instance, if you get this distance after the integration, your system will not explode. As in, for instance, if you use Lennard-Jones potential, if your time step is a little bit bigger, you can go to this distance, and then your force will go to the infinite, and the world will explode. Yeah, closer. And this idea, but obviously, this is not indicated for atomic simulation. This is for mesoscale simulations. So I modeled, for instance, we're using DPD, an entire cell, biological cell, moving in the extracellular matrix. Yeah. And then you can parameterize, basically, the two parameters for the force is just this distance and the maximum force. And well, and now we are finishing another work using this approach to study water-oil separation using nanorods, and you can build a system with like 1 micrometer for which one micrometer. So really huge systems. This is the idea. Questions? No? Thank you.